Hear me? So, hi, my name is Rani. I'm a security researcher at the Imperium. I'm super excited to be here. It's really my honor to be in ShakaCon, first time in Hawaii. And today I'll speak about my own experience within iOS research. To be honest, all the information I'm going to share with you today is few months that I'm learning how iOS operating system works. And when I started the research, I was really newbie to iOS. So basically, I came to iOS and mobile research after a few years of experience with different platforms. So what I really want to show you today is how you can conduct the same research methodologies even to iOS, which is repeatedly, for some reason, known as complicated. So what are we going to cover today? I'll use this one. We will have we'll start by covering some basic terms over iOS, specifically over the iOS containerization, also known as the Sandbox. And we will cover digit cache, which is an important file for the research I conducted. And a few words about LaunchD. Basically, we can have a whole presentation only on LaunchD. And specifically over Mach messages. I will share with you some of the difficulties I had over iOS and my own research on MediaServerd and Bluetooth, and whether they're going to be ETA soon. But actually, there was already jailbreak released, so no. So let's start. I'm Rani Idan, as already said. I'm a security researcher at the Imperium, Z-Labs team. I'm director of platforms research. I live in Tel Aviv, in Israel. Basically, this means I'm going to the beach probably every weekend. And by the way, it took me 30 hours to get here. So yeah, it was really tough. I can't recover from the jet lag. Anyway, and I'm an iOS researcher, and I decided to put it in different bullet just to explain it again. This was all new area to me. So everything I'm telling you here, go and do it for yourself and learn new things. So iOS, only a rough overview, evolved from OS X and is based upon Darwin operating system. In many ways, you can find a lot of overlapping code between iOS and all the other OS devices, including macOS and watchOS. That's why it might be interesting to choose a attack surface that might be also true for all the other platforms. In my case, it wasn't for macOS. And the XNU kernel, the iOS is based upon the XNU kernel, which all the sources are publicly available, which is a really strong reference. I think this is the most important reference you can have over iOS. And iOS strictly enforces the sandbox limitations. And just I want to put another term that I'm really sure that most of you already know, is the jailbreak. It is a process which means a full execute of read and write that is obtained over the system partition. It is done in a lot of ways. This is not what we're going to talk about today. Okay, now let's have an overview over just a really rough overview, and really I try to flatten it. We can logically separate it into three different parts. We have the application, core services, and the kernel. Basically, what it means that the application are the sandbox profile. One application wishes to use, in our case, YouTube will want to decode some frames. It will use the Video Toolbox API and ask for one of the core services, in that case MediaServerd, to handle the request. And MediaServerd, on the behalf of YouTube, will use one of the IO key drivers on the kernel side. So I think it's important to say at this point that also the core services are operated and restricted by different sandbox profiles. That means MediaServerd D will not be able to access Bluetooth D if it doesn't need to. So if you're choosing an attack surface, you will want to choose an attack surface that has the much larger impact from an application over to the kernel. So in order to improve some performance, Apple decided to take all the system libraries and combine it into one big file that is being loaded to each process, and it's called the D shared cache. Basically, you can find the equivalent in Windows, I don't know, like kernel 32 DLL. All system libraries are combined, both the public SDK or the private. The file size is approximately 700 megabytes. We will understand later why it's actually a huge problem. And there are several ways to analyze. I'm using IDA or J2. You can find a lot of open source tools out there. And so what is IPC? And again, in the aspect of iOS, it is used to communication between processes. Apple decided to implement several IPC mechanisms, such as XPC, Mach messages, and distributed objects. And they are all based upon Mach messages. That means the cornerstone of all the Apple's IPC are the Mach messages. So I found it really interesting to fully understand Mach messages, and basically I couldn't really read the references they have on the man page because it's not going to help. So in that case, it was just reading the kernel source code and understanding Mach messages. And Apple also decided to implement all the well-known POSIX IPC. And like I said, it relies on Mach messages. So what are Mach messages? It's used within the kernel and user mode. In order to send Mach message, you need to use the Mach message trap syscall. And let's go through several fields in the struct. We have the message bits. It's a field used to set the type of the message. The sender of the message may specify if the message is complex. If the message is complex, that means you can also send data. The data is going to be added after the header, and the remote port basically specifies the recipient of the message, the destination of the message. The local port is actually an auxiliary port, which you can tell the recipient to which port to return the message. And there is the message ID, which is conventionally used to convey which function to invoke on the side of the server. Basically, it's just a number that the recipient can use to decide which function it needs to use. So, okay, we have this struct, but in order that processes will be able to locate each other and get the remote port, they are going to need someone to resolve some kind of constant name to a remote port. That's why we're using LaunchD. LaunchD in practice is a unified service management framework. Basically, that means, and again, I'm really flattening LaunchD. It's used to start new demos or kill them. It's basically the watchdog from the user mode space. So when a process wishes to check in as a new Mach server, it's going to use the bootstrap check-in function and going to ask from LaunchD to hold that Mach port, and eventually process B will be able to call bootstrap lookup with the same name and get from LaunchD the Mach port that it will communicate. and eventually both of the processes are going to communicate between each other without using a launch-T. So while I was researching iOS, I had several difficulties. I think it's worth to mention some of them. Basically, the device is jailed. That means you cannot really have any utility like a DB or debug processes. You cannot attach debugger to any of the signed daemons. That means most of the time you're going to use the device console or the crash reports if you manage to crash a daemon and you're trying to debug it in order to exploit a vulnerability. And you cannot flash old versions. That's why you need to have on your desktop just a bunch of devices. And Apple don't really care to document anything that is not for the developers. That means you cannot really have any insight of the internal documentation. That's why you need some people in the community that are sharing their knowledge. And the shared cache was just enormous for IDA. So it might sound a really weird bullet, but it was really a headache. I had to buy a lot of RAM sticks and create a huge workstation. And until finally IDA fixed their issues with the shared cache and they started to handle it properly in the aspect of memory management. Sorry. And while working on the shared cache, I just had to have a lot of precautions, like not trying to reference between functions, basically because IDA will just crash. So, what is a sandbox escape? Basically, it means generally sandbox escape is a type of vulnerabilities that gives the attacker executing malicious code on behalf of elevated process, such as the daemons. So, in our case, we are a malicious application with a nice icon there, and we intending to gain malicious code execution over one of the services. The reason why we want to do this is to widen our attack surface to the kernel, because eventually, of course, it is possible to find a vulnerability and to exploit it from malicious application directly to the kernel. However, it's much more easier, you might say, if you already being able to execute malicious code over one of the services. So, and eventually from that core services to gain access to the kernel. So at this moment, I got some overview over iOS, and I decided to start choosing my next target. So I used SBTool by Jonathan Levin, and basically what SBTool does is just a tool that can be used in order to inspect the sandbox profile of processes while using it with a MAC argument with the PID. You can just compile regular application to check which MAC servers are accessible from within the sandbox. So today we are going to focus over two different daemons, which are the Apple Core Media decompression session, which is being executed under MediaServerd, and Apple Server Bluetooth, which is being executed under Bluetooth. And both of them were interesting to me because specifically Bluetooth, because it's communicating with a lot of other processes, which has a lot of impact, and we will see it later on the last vulnerability. So from that point, it was all about just taking the strings of the MAC messages, MAC servers, and searching them in the shared cache. And from the shared cache, it was just a matter of referencing a little and finding where they are initializing the new MAC server. So let's have a look over the initialization of the decompression session server in MediaServerd. There are few arguments. The first argument is the name of the server, and the third argument is the handler for each message that is being received under the decompression session MAC server. Internally, FigRPC start server is going to call bootstrap check-in and will register an event handler with the, how it's called? VT decompression session server struct. Sorry, it's function. So let's have a look over this function, this MAC messages handlers. So the first thing you have to see is that there are two arguments for the function, the in and out message, and it's going to take the in message, taking the message ID, subtracting some constant value, and eventually going to check if it's below or equal some number, which is the number of handlers that are available for this server, and it's going to acquire the handler address, the actual pointer for the function, and eventually it's going to call it. So the first thing was to just enumerate over the handlers and see which handlers are accessible for us from within the sandbox. So it was diving into this VT decompression session subsystem struct, and this struct is basically just an array of different function addresses. So sorry. So I decided to focus on X decode frame, which was basically the actual logic of the decompression session. And what XDecode frame, the XDecode frame parameters are just an in and out message. So let's dive into XDecode frame. XDecode frame basically is the backend of VT decompression session decode frame API call. It is, again, accessible from within the sandbox, and it's used to decode frames from serialized buffer. And eventually it's going to return message with the result code back to the client, back to the application. So it looked like a real nice attack surface, to my opinion at least. So I decided to have a look over the serialization process. And the main goal I had in mind was just to take manual analysis over the serialization process, intercepting legitimate buffers, because I'm lazy, for going through reversing all of the branches there are, and modify and corrupting each serialized buffer, and eventually replying it back to MediaServerd. And hopefully I will find just a bunch of vulnerabilities there. So let's have an overview over the decompression process. First, when application wants to use the decompression session, it's going to call the session create API call. It's going to send the MAC message with all the request parameters to MediaServerd. On MediaServerd side, this message is going to be handled by the xCreate callback. Afterwards, when application wants to decode some frame, it's going to serialize that frame, send it with MAC message to XDecode frame, and the serialization process was just about reversing the function, this long name, create sample buffer from serialized blah, blah, blah. And it's just a regular TLV, or in that case, LTV, type length value, serialization. And the struct is pretty simple and easy. We have 4 bytes that are declaring the size of the next node, 4 bytes of the type of the node, and it's going nested to each node. So basically, all I had to do was to implement this serialization process. I did it on Python, just so I could play with it manually or fuzzing it automatically. And I did, and I also implemented it on C, so I could create an application that will start sending serialized buffers directly without all of the API checks. So what I was trying to do, again, it was the intercept, modify, and replay. So all I had to do is just intercepting legitimate serialized buffers, modifying those buffers on different places, maybe the size, maybe the actual content. It was never interesting to modify them on the type of the node, and eventually replaying it back to XD code frame. So what I did here was, again, first time I ever tried to do anything on iOS. So I just decided to fuzzing, because it might work, and I want to realize if I'm having at least any case with this research. So what came out of it was actually about 3,032 crashes, and when I went through the crashes, I came out with 31 unique crashes. It's a lot. It means a lot to me. And I started to manually analyze each one of them, and I came with some stray asserts Apple forgot there, some nutty references, some use after free bugs, some out-of-bounds read or write. So it was really great success for me. And it was about iOS 10.3, I think. And while I was heading to Vegas to just regular conferences, waste of time, in Vegas, I saw that Apple decided to refactor some of MediaServerd, along with some iPad multitasking stuff. So I decided to check my POC code and see if anything is working. But no, Apple decided to refactor all of their callbacks for some reason. And I ended up with nothing, probably. So what I decided to do was just, instead of going through MediaServerd again, was just to continue to the next daemon, because if I achieved that much only in a few months, I can do much more in Bluetooth-D. So Bluetooth-D was rebranded from MediaServerd. It implements the Bluetooth stack on the user mode side. Each process with Bluetooth diamond communication using Bluetooth-D, and it is some kind of trusted broker or core service. So again, in order to understand if this is a legitimate attack surface, I had to understand whether Bluetooth-D is using a lot of IO-kit communication, and I found that indeed Bluetooth-D has a lot point of context between Bluetooth-D and all the other core services, and Bluetooth-D and the kernel. So I just took my IDA Python skills and improved it a little, and I came out with a way to automate all of the Mach message handler sending messages, and I could just extract all the handlers with all the arguments to each Mach message struct, so I could easily automate the process. Now let's dive into two different callbacks I had, which are the BT local device get pair devices. Again, just to put it in, this Mach handler is being executed under Bluetooth-D. And it's getting two parameters, again, the in and the out message, just like in MediaServerd. And let's dive into the internal implementation of get pair devices, which is getting as fifth argument data that is absolutely controlled by us, by Sandbox application. So take a look at it. Maybe you will find what's going on here. So let's go through it. The fifth argument is controlled by us. And afterwards, it's going to do something that was pretty odd at first sight. It's going to reference the first local variable on the stack, subtracting from that address data that is absolutely controlled by us. And eventually it's going to put it in some pointer on the stack. So what Apple tried to do here was to dynamically allocate array on the stack. And let's have a look over the disassembly of it. We can see that they are taking the fifth argument, taking the stack pointer, which is the first local variable, subtracting from the stack pointer data that is controlled by us, and just putting it back in the stack pointer. So it just means that we have full control over the stack pointer relatively. So I disclosed it to Apple, and Apple acknowledged it as relative control over the stack pointer, and it eventually could lead to an info leak inside of the internal implementation of the get-paired devices. And the same bug is exists on all of the in 6 different Mac callbacks. So Apple fixed it, and they fixed it just by checking the size of the data that is controlled by us, which they limited it to 100 hex. So let's stop for a moment and understand how Bluetooth communication is working with its client. So Bluetooth just holds a list of all the attached clients, just like the other daemons or even regular applications. And whenever application or a daemon wishes to use Bluetooth capabilities, it's going to call BT session attach, and Bluetooth will hold all of the session information within Bluetooth memory. And afterwards, as part of the initialization process, SharingD will ask from, and pay attention to this one, it's going to call BT local device head callbacks. Basically, it's going to ask from Bluetooth to hold address of the event callback handler in the address space of SharingD. And it's going to hold that address within Bluetooth memory. So whenever an event is going to be called, when SharingD attached to Bluetooth, and Bluetooth finds a new event that it needs to notify SharingD, it's going to tell SharingD what is the handler for each event message. So let's have a look over the BT local device add callbacks implementation. So the add callbacks internal implementation is just getting 3 parameters that are fully controlled by us, by the attacker. And basically, it's the session token, it's the address that we want to register, and the actual data. So I decided to take a look over the session because it seemed weird to me. We just saw that in MediaServerd they decided to check to check the session by the local port, and here they're using some session token. So how are they verifying the session? Basically, they're just taking the session token and enumerating over all of the sessions and checking if the session token exists in all of the sessions. If not, it's going to return 7, which is, I don't know which session it is. So I had an idea. Let's try as a malicious application. Let's try to add callbacks and to brute force that session token. If I'm succeeding, I'm being able to let Bluetooth add new callback that may be invoked, add new callback on the address space of another process, and I will allegedly be able to make other daemons jump to arbitrary address that is controlled by me. So I took a look over the session token initialization process, and I found out that basically, this is all I needed to brute force the token, just 2 bytes and some 1 bit that is changing. So basically, this is all the POC code for the next one. So I decided to execute it. And the results were just, how would I call it, weird. Because what happened next was, I got on the crash reports that all of the daemons on the iOS device just crashed, and they all jumped to address that was just controlled by me, and I also had control over a few of the registers. So basically, that's it. It was that easy. And Apple decided to fix this one with initializing the session token with some random 32 bit instead of 2 bytes. So they changed it a little. And now to probably a question I got a lot on Twitter, is it going to be jailbreak? Then no, there are new ones. And there are some references I think that you should all know if you're willing to start researching over iOS. You can find a more extensive code of the POC of the last vulnerability on my GitHub. And I want to share some credits to a few colleagues. First, Zimperium for the paycheck, Jonathan Levine for making a lot of great references, Adam, Tamir, and Nikias, which are colleagues from my team. And basically, that's it. Thank you. And if you have any questions. So thank you.